Imagine a spacecraft built to withstand temperatures hotter than molten lava, diving closer to the sun than any human-made object ever has. This is the Parker Solar Probe, a mission that has not only pushed the boundaries of human engineering, but has also uncovered secrets that challenge everything we thought we knew about our star. What if I told you that some of these discoveries defy the laws of physics as we understand them? Today, we're diving into 25 unexplained space anomalies revealed by the Parker Solar Probe, each one more baffling than the last. From the sun's mysterious corona to its connection with cosmic rays, these findings are rewriting the textbooks of astrophysics. But here's the kicker: despite all the data we've gathered, the sun still holds secrets that leave even the brightest scientists scratching their heads. By the end of this video, you'll not only learn about these cosmic mysteries but also understand why they matter to us here on Earth. So, buckle up, because we're about to take a journey into the heart of our solar system, where the answers are as elusive as the questions are profound. Stay with us and let's unravel the mysteries of the Parker Solar Probe together. Now, let's zoom in on the first of these cosmic puzzles, the sun's mysterious corona. The Parker Solar Probe has brought us closer than ever to understanding this enigmatic outer layer of the sun, but what it found has only deepened the mystery. The corona, the sun's outer atmosphere, is scorching hot, millions of degrees hotter than the sun's surface itself. This defies everything we know about heat and energy. If you think about it, it's like walking away from a campfire and feeling the air get hotter the farther you go. It just doesn't make sense. Scientists have long been baffled by this phenomenon, and the Parker Solar Probe's data has only added more layers to the puzzle. One leading theory suggests that tiny explosions called nanoflares, happening all over the sun's surface, could be heating the corona. Another idea points to magnetic waves transferring energy from the sun's interior to its outer layers. But here's the catch: neither theory fully explains the extreme temperatures observed. The probe's measurements have revealed complex magnetic structures and energy flows that we're still struggling to interpret. What's clear is that the corona holds secrets that could revolutionize our understanding of not just the sun, but of stars across the universe. And as we continue to analyze the data, one thing is certain: the sun's corona is a reminder that even our closest star is still full of surprises. Moving on to our next cosmic puzzle, let's dive into the mystery of solar wind acceleration. The Parker Solar Probe has given us an unprecedented look at how particles in the solar wind behave, and what it found has left scientists scratching their heads. Solar wind, a stream of charged particles flowing from the sun, is something we've known about for decades. But here's the twist: these particles don't just drift away from the sun at a steady pace. Instead, they accelerate to supersonic speeds, reaching velocities that defy our current understanding of physics. Imagine throwing a ball into the air, only to watch it suddenly rocket forward faster than the speed of sound. That's the kind of unexpected behavior we're talking about. The probe's observations show that the solar wind doesn't just gradually pick up speed as it moves away from the sun. Instead, it undergoes sudden bursts of acceleration, reaching speeds of hundreds of kilometers per second. This challenges the traditional models that suggest the solar wind should slow down as it travels further from the sun's gravitational pull. One theory suggests that magnetic fields near the sun's surface might be acting like slingshots, flinging particles outward at incredible speeds. Another idea points to turbulence in the sun's atmosphere, creating waves that push the particles faster and faster. But here's the catch: neither explanation fully accounts for the extreme speeds observed. What makes this even more intriguing is that the solar wind isn't just a curiosity, it has real-world implications. These high-speed particles can affect everything from satellite communications to power grids on Earth. Understanding how and why they accelerate could help us better predict and prepare for their impact. The Parker Solar Probe's data is giving us clues, but the full picture remains elusive. As we continue to analyze these findings, one thing is clear. The Sun's solar wind is another reminder that even the most familiar cosmic phenomena can still surprise us. And with every new discovery, we're one step closer to unraveling the mysteries of our star and the universe beyond. Now, let's turn our attention to another baffling discovery: magnetic field switchbacks. These sudden reversals in the Sun's magnetic field are unlike anything scientists expected, and they might hold the key to understanding even more about our dynamic star. Now, let's shift our focus to one of the most puzzling phenomena the Parker Solar Probe has uncovered: magnetic field switchbacks. These sudden, unexpected reversals in the Sun's magnetic field have left scientists both fascinated and perplexed. Picture this: you're driving down a straight road, and suddenly, without warning, the road twists and turns in the opposite direction. That's essentially what's happening with the Sun's magnetic field. These switchbacks are sharp, zigzagging changes in the magnetic field's direction, and they occur much more frequently than anyone anticipated. The Parker Solar Probe's instruments have captured these switchbacks in stunning detail, revealing that they are not rare events but rather a common feature of the Sun's magnetic environment. What's even more surprising is the scale of these reversals. Some switchbacks span thousands of kilometers, and they happen so quickly that they seem to defy the laws of physics as we understand them. Scientists are still trying to figure out what causes these dramatic flips. One leading theory suggests that they might be caused by magnetic reconnection events, where the Sun's magnetic field lines break and reconnect, releasing enormous amounts of energy. Another idea points to turbulence in the Sun's atmosphere, creating ripples that twist and flip the magnetic field. But why do these switchbacks matter? For one, they could play a crucial role in heating the Sun's corona, the outermost layer of its atmosphere, which is inexplicably hotter than the surface below. They might also help explain how the solar wind accelerates to such incredible speeds, as we discussed earlier. Some researchers believe that switchbacks could act like magnetic springs, propelling particles outward with tremendous force. If this is true, it could revolutionize our understanding of how energy and particles move through the solar system. The implications of these findings go beyond just the Sun. Magnetic fields are a fundamental force in the universe, shaping everything from the behavior of stars to the formation of galaxies. Understanding how they behave in such extreme environments could shed light on similar processes happening in other parts of the cosmos. The Parker Solar Probe's observations are opening up entirely new avenues of research, challenging us to rethink what we know about magnetic fields and their role in the universe. As we continue to study these magnetic field switchbacks, one thing is certain: they are a reminder of how much we still have to learn about the Sun. Each new discovery brings us closer to understanding the complex and dynamic nature of our star, and with every twist and turn, the Parker Solar Probe is rewriting the rules of solar physics. Next, we'll explore another intriguing anomaly: the dust-free zone near the Sun, a region where interplanetary dust seems to vanish into thin air. Now, let's turn our attention to another baffling discovery made by the Parker Solar Probe: the dust-free zone near the Sun. Imagine a vast, empty space where the usual cosmic debris simply disappears. This is exactly what the probe has observed in a region close to our star, where interplanetary dust, which is typically abundant throughout the solar system, seems to vanish without a trace. It's as if the Sun has created an invisible barrier, sweeping away all the dust particles in its vicinity. Scientists have long known that interplanetary dust is a common feature of our solar system. Tiny particles, often no larger than a grain of sand, float through space, reflecting sunlight and sometimes even creating the faint glow known as zodiacal light. But as the Parker Solar Probe ventured closer to the Sun, it detected something unexpected: a zone where this dust simply doesn't exist. This region, extending roughly 3.5 million miles from the Sun's surface, is eerily clean, devoid of the dust that fills the rest of the solar system. So, what's causing this dust-free zone? One leading theory suggests that the intense heat near the Sun vaporizes the dust particles before they can accumulate. At such close proximity, temperatures soar to millions of degrees, enough to turn solid particles into gas almost instantly. Another possibility is that the Sun's powerful magnetic fields and solar wind act like a cosmic broom, sweeping the dust away and preventing it from settling in this region. Some researchers even speculate that the dust particles might be pushed outward by the pressure of sunlight itself, a phenomenon known as radiation pressure. But why does this matter? Understanding this dust-free zone could provide valuable insights into the Sun's influence on its surrounding environment. It might also help us better predict how dust behaves in other star systems, especially those with planets in the habitable zone. For example, if dust can't survive near a star, it could affect the formation of planets or even the conditions necessary for life to emerge. The Parker Solar Probe's findings are challenging our assumptions about how dust interacts with stars, and they're opening up new questions about the dynamics of our solar system. As we continue to explore this mysterious dust-free zone, one thing is clear: the Sun still holds many secrets. Each new discovery, like this one, reminds us of how much we have yet to learn about our closest star. Next, we'll dive into another intriguing anomaly, the unexplained plasma waves detected by the probe, which might hold the key to understanding how the solar wind accelerates to such incredible speeds. Now, shifting our focus to another fascinating discovery, let's explore the unexplained plasma waves detected by the Parker Solar Probe. These waves, rippling through the Sun's atmosphere, have left scientists both intrigued and puzzled. Unlike the familiar waves we see in water or hear in sound, these plasma waves are made up of charged particles moving in rhythmic patterns, creating oscillations that defy our current understanding of solar physics. What makes these waves so unusual is their behavior. The Parker Solar Probe observed them moving at incredibly high speeds, far faster than predicted by existing models. These waves seem to travel outward from the Sun, almost as if they're riding on the solar wind, the stream of charged particles constantly flowing from the Sun's surface. But here's the twist: these waves don't just move passively. They appear to play an active role in accelerating the solar wind itself, pushing particles to supersonic speeds that baffle researchers. One theory suggests that these plasma waves act like a cosmic slingshot, transferring energy to the solar wind particles and propelling them outward. Imagine a surfer catching a wave. The wave provides the energy needed to move forward. In a similar way, these plasma waves might be giving the solar wind particles the boost they need to reach such extraordinary velocities. Another possibility is that the waves are generated by magnetic interactions within the Sun's atmosphere, creating a feedback loop that amplifies both the waves and the solar wind. But why does this matter? Understanding these plasma waves could unlock the secrets of how the solar wind accelerates, a process that has remained a mystery for decades. The solar wind isn't just a curiosity. It shapes the entire solar system, influencing everything from the auroras on Earth to the conditions in deep space. If we can figure out how these waves work, we might gain new insights into the Sun's influence on its surroundings and even improve our ability to predict space weather, which can affect satellites, astronauts, and communication systems. As we delve deeper into this anomaly, one thing becomes clear: the Sun's atmosphere is far more dynamic and complex than we ever imagined. These unexplained plasma waves are just one piece of a much larger puzzle, reminding us that every discovery brings us closer to understanding the true nature of our star. Next, we'll examine another intriguing phenomenon, the Sun's differential rotation, and how it challenges our current theories about how stars spin. Now, turning our attention to another puzzling aspect of the Sun, let's dive into the mystery of its differential rotation. Unlike Earth, which rotates as a solid body, the Sun spins at different speeds depending on where you look. At its equator, the Sun completes a full rotation in about 25 days, but near its poles it takes closer to 35 days. This phenomenon, known as differential rotation, has been observed for decades, but the Parker Solar Probe's data has revealed new complexities that challenge our understanding of how stars behave. The probe's measurements show that the Sun's rotation isn't as straightforward as we once thought. While scientists expected the rotation rates to vary smoothly from the equator to the poles, the data suggest abrupt changes in speed at certain latitudes. These irregularities don't align with current models, which assume a more gradual transition. This raises questions about what's driving these variations and whether there's something deeper happening beneath the Sun's surface that we're not yet aware of. One leading theory is that the Sun's internal magnetic fields play a significant role in shaping its rotation patterns. Magnetic forces could create zones of faster or slower rotation, disrupting the smooth flow we'd expect. Another possibility is that the Sun's internal structure, including its layers of plasma and convection currents, interacts in ways we don't fully understand. These interactions might generate the uneven rotation rates observed by the Parker Solar Probe. Why does this matter? Differential rotation isn't just a quirk of the Sun, it's a key factor in solar activity. The varying rotation speeds can twist and stretch the Sun's magnetic fields, leading to phenomena like sunspots, solar flares, and coronal mass ejections. By studying these rotation patterns, scientists hope to better predict solar activity and its effects on space weather, which can impact everything from satellite communications to power grids on Earth. As we piece together the puzzle of the Sun's differential rotation, one thing is certain: our star is far more dynamic and intricate than we ever imagined. The Parker Solar Probe's findings are pushing the boundaries of solar physics, forcing us to rethink long-held assumptions about how stars rotate. Next, we'll explore another anomaly that continues to baffle researchers: the Sun's solar flare predictions and why they often miss the mark. Moving forward, let's explore another fascinating mystery uncovered by the Parker Solar Probe: solar flare predictions and why they often fall short. Solar flares are among the most dramatic and energetic events in our solar system, releasing bursts of radiation that can disrupt satellites, communications, and even power grids on Earth. Predicting these eruptions is crucial for protecting our technology and infrastructure, but despite decades of research, our models still struggle to get it right. The Parker Solar Probe has provided unprecedented data on the conditions leading up to solar flares, revealing gaps in our understanding. Current prediction models rely on tracking sunspots, dark, cooler regions on the Sun's surface where magnetic fields are particularly strong. These sunspots are often the birthplaces of solar flares, but the probe's observations show that not all sunspots behave the same way. Some produce massive flares, while others remain eerily quiet, and scientists are still trying to figure out why. One of the key challenges is the complexity of the Sun's magnetic fields. The probe's measurements suggest that the magnetic energy stored in these fields doesn't always release in predictable ways. Sometimes the energy builds up and dissipates gradually, while other times it erupts suddenly in a violent flare. This unpredictability makes it difficult to pinpoint exactly when and where a flare will occur. Another factor complicating predictions is the Sun's dynamic environment. The probe has observed that small-scale interactions between magnetic fields and plasma can trigger flares unexpectedly. These interactions are often too subtle for current instruments to detect in advance, leaving scientists scrambling to update their models with new data. It's like trying to predict a thunderstorm by only looking at the clouds. There's so much happening beneath the surface that we can't see. So why does this matter? Accurate solar flare predictions are essential for safeguarding our increasingly technology-dependent world. A single powerful flare could knock out GPS systems, disrupt air travel, or even cause widespread blackouts. By improving our understanding of the sun's behavior, we can develop better warning systems and mitigate the risks posed by these cosmic outbursts. The Parker Solar Probe's findings are shedding light on the intricate processes behind solar flares, but they're also revealing just how much we still have to learn. As we continue to analyze the data, one thing is clear: the sun is full of surprises, and each discovery brings us closer to unraveling its secrets. Next, we'll delve into another enigma that has puzzled scientists for decades: the mystery of the missing solar neutrinos. Now, let's turn our attention to one of the most perplexing mysteries in solar science: the case of the missing solar neutrinos. Neutrinos are tiny, nearly massless particles produced in vast quantities by nuclear reactions in the sun's core. According to our understanding of solar physics, the sun should emit a specific number of these particles, but for decades, experiments on Earth have detected far fewer than expected. This discrepancy has puzzled scientists and even led some to question whether we truly understand how the sun works. The Parker Solar Probe hasn't directly measured neutrinos. Its instruments aren't designed for that, but its findings have provided crucial context for this mystery. The probe's data on the sun's core conditions, such as temperature and pressure, have confirmed that the nuclear reactions producing neutrinos are occurring as predicted. So, if the sun is generating the right number of neutrinos, why aren't we detecting them all? The answer lies in the strange behavior of neutrinos themselves. These particles are incredibly elusive, rarely interacting with matter. In fact, trillions of neutrinos pass through your body every second without you noticing. But their elusiveness isn't the only challenge. Neutrinos come in three types or flavors: electron, muon, and tau neutrinos, and they can change from one flavor to another as they travel through space. This phenomenon, known as neutrino oscillation, means that by the time neutrinos reach Earth, many of them have transformed into types that earlier detectors couldn't detect. This discovery revolutionized our understanding of particle physics and solved part of the mystery. However, even with neutrino oscillation accounted for, there's still a small gap between the predicted and observed numbers. Some scientists speculate that this could point to an even deeper mystery, perhaps a fourth type of neutrino known as a sterile neutrino that doesn't interact with matter at all. Others suggest that our models of the sun's core might still be missing something, like an unknown process affecting neutrino production. The implications of this anomaly go beyond the sun. Neutrinos are produced in many cosmic events, from supernova to black hole collisions, and understanding their behavior could shed light on the fundamental workings of the universe. The Parker Solar Probe's insights into the sun's core are helping refine our models, but the mystery of the missing neutrinos reminds us that even the most well-studied star in the universe still holds secrets waiting to be uncovered. Next, we'll examine another surprising discovery: the probe's measurements of the sun's magnetic field strength, which have challenged long-held assumptions. Now, shifting our focus to another groundbreaking discovery, let's dive into the sun's magnetic field strength, a topic that has left scientists scratching their heads. The Parker Solar Probe has revealed measurements of the sun's magnetic field that don't align with what we thought we knew. For decades, our understanding of the sun's magnetic field was based on models and indirect observations, but the probe's direct measurements have turned those assumptions upside down. The sun's magnetic field is incredibly complex, shaping everything from solar flares to the solar wind. It's generated by the motion of charged particles in the sun's interior, creating a dynamic and ever-changing force. Previous estimates suggested that the magnetic field strength near the sun's surface would follow a predictable pattern, but the Parker Solar Probe's data shows something entirely different. The field is far more variable and intense in certain regions than scientists anticipated, with fluctuations that defy existing models. One of the most surprising findings is the presence of localized magnetic hotspots, areas where the magnetic field is significantly stronger than the surrounding regions. These hotspots appear to play a key role in accelerating the solar wind, the stream of charged particles that flows outward from the sun. But how these hotspots form and why they're so concentrated remains a mystery. Some researchers speculate that they could be linked to the sun's turbulent interior, where swirling plasma generates magnetic fields in ways we don't yet fully understand. The implications of these findings are profound. The sun's magnetic field doesn't just influence solar activity, it also affects space weather, which can impact satellites, communication systems, and even power grids on Earth. If our models of the sun's magnetic field are incomplete, it means our ability to predict space weather events is also limited. The Parker Solar Probe's data is helping scientists refine these models, but the unexpected variability in the magnetic field strength suggests there's still much to learn. This anomaly raises intriguing questions about the sun's inner workings. Could there be unknown processes in the sun's core that amplify the magnetic field in unexpected ways? Or are we missing a fundamental piece of the puzzle when it comes to how magnetic fields are generated in stars? As the Parker Solar Probe continues its mission, each new measurement brings us closer to answering these questions and perhaps uncovering even more surprises. Next, we'll explore another puzzling phenomenon, irregularities in the sun's 11-year cycle, and how the probe's data is reshaping our understanding of this cosmic rhythm. Now, let's turn our attention to one of the sun's most fascinating rhythms, the solar cycle. For centuries, scientists have observed that the sun follows an approximately 11-year cycle, marked by periods of intense activity and relative calm. This cycle is characterized by the rise and fall of sunspots, solar flares, and other phenomena. But the Parker Solar Probe's latest findings suggest that this cycle might not be as predictable as we once thought. The solar cycle is driven by the sun's magnetic field, which flips polarity roughly every 11 years. During the cycle's peak, known as solar maximum, the sun becomes a hive of activity with frequent solar flares and coronal mass ejections. At the cycle's low point or solar minimum, the sun quiets down with fewer sunspots and less magnetic activity. For decades, this pattern seemed consistent, but the Parker Solar Probe's data has revealed irregularities that challenge our understanding. One of the most striking anomalies is the timing of the cycle. While the 11-year pattern has been a cornerstone of solar physics, the probe's observations suggest that the cycle's duration can vary more than previously believed. In some cases, the transition between solar minimum and maximum appears to happen faster or slower than expected, with no clear explanation. This variability raises questions about what drives the cycle and whether external factors, such as the sun's interaction with the rest of the solar system, could be influencing it. Another puzzling discovery is the uneven distribution of solar activity during the cycle. Traditionally, scientists expected the sun's activity to be relatively symmetrical, with sunspots and flares distributed evenly across its surface. However, the Parker Solar Probe has detected regions where activity is concentrated in unexpected ways, creating hotspots of solar phenomena that don't align with the cycle's typical progression. These hotspots could be linked to the sun's internal dynamics, but their exact cause remains unclear. The implications of these irregularities are significant. The solar cycle plays a crucial role in shaping space weather, which affects everything from satellite operations to Earth's climate. If the cycle is less predictable than we thought, it could complicate efforts to forecast space weather events, potentially leaving us unprepared for solar storms that could disrupt technology and infrastructure. The Parker Solar Probe's data is helping scientists refine their models, but the anomalies it has uncovered suggest that our understanding of the solar cycle is far from complete. As we continue to study the sun, these irregularities remind us that even the most well-established patterns in nature can hold surprises. What other secrets might the solar cycle conceal, and how might these discoveries reshape our understanding of the Sun's influence on our solar system? Next, we'll explore another intriguing anomaly: unexpected gravitational effects observed by the Parker Solar Probe and their potential implications for astrophysics. Now, shifting our focus to another layer of the Sun's mysteries, let's dive into the unexpected gravitational effects observed by the Parker Solar Probe. Gravity, as we know it, is a fundamental force that governs the motion of celestial bodies, and the Sun's immense gravitational pull is what keeps our solar system together. But the probe's findings have revealed anomalies in the Sun's gravitational behavior that challenge our current understanding of astrophysics. One of the most surprising discoveries is the subtle variations in the Sun's gravitational field. According to Newton's laws of motion and Einstein's theory of general relativity, the Sun's gravity should follow a predictable pattern, decreasing steadily with distance from its core. However, the Parker Solar Probe has detected slight deviations from this expected pattern, particularly in regions close to the Sun's surface. These deviations suggest that there may be unseen factors at play, possibly related to the Sun's internal structure or the influence of its magnetic field. Another intriguing observation is the probe's detection of gravitational waves, ripples in spacetime caused by massive objects accelerating. While gravitational waves are typically associated with events like black hole mergers or neutron star collisions, the Parker Solar Probe has picked up faint signals that could be linked to the Sun's own activity. These signals are much weaker than those detected by observatories like LIGO, but their existence raises questions about how the Sun's dynamic processes might generate such waves. Could the Sun's internal turbulence or its magnetic interactions be producing these ripples? If so, what does this mean for our understanding of gravity itself? The implications of these gravitational anomalies are profound. If the Sun's gravity doesn't behave exactly as predicted, it could force us to rethink some of the foundational principles of astrophysics. For instance, it might require adjustments to our models of stellar evolution, or even lead to new insights into the nature of dark matter and dark energy, which are thought to influence the universe's gravitational framework. The Parker Solar Probe's data is opening up new avenues of research, challenging scientists to explore these anomalies and their potential impact on our understanding of the cosmos. As we continue to unravel the Sun's gravitational secrets, one thing is clear: even the most fundamental forces in the universe can hold surprises. What other gravitational mysteries might the Sun conceal, and how might these discoveries reshape our understanding of the universe's most basic laws? Next, we'll explore another fascinating anomaly: the boundary of the Sun's heliosphere and its unexpected properties. Now, let's venture beyond the Sun's immediate influence and into the vast expanse of its heliosphere, the bubble-like region of space dominated by the Sun's solar wind and magnetic field. This boundary, where the Sun's influence wanes and interstellar space begins, has long been a subject of fascination. But the Parker Solar Probe's findings have revealed that this boundary is far more complex and dynamic than we ever imagined. One of the most striking discoveries is the irregular shape of the heliosphere's boundary. Instead of a smooth, symmetrical bubble, the probe's data suggests that the boundary is uneven and distorted, almost like a comet's tail being pushed and pulled by interstellar winds. This asymmetry challenges the traditional view of the heliosphere as a uniform shield protecting our solar system from cosmic radiation. What's causing this distortion? Scientists believe it could be due to the pressure of interstellar gas and magnetic fields, but the exact mechanisms remain unclear. Another unexpected finding is the presence of turbulent waves at the heliosphere's edge. These waves, detected by the probe, appear to be generated by the interaction between the Sun's solar wind and the interstellar medium. This turbulence creates a chaotic environment where particles and energy are exchanged in ways that defy our current models. Could this turbulence be influencing the flow of cosmic rays into our solar system? And if so, how does this affect the protective role of the heliosphere? Perhaps the most puzzling aspect of the heliosphere's boundary is its permeability. The Parker Solar Probe has observed that certain particles and energy from interstellar space can penetrate this boundary more easily than previously thought. This raises questions about how effectively the heliosphere shields our solar system from harmful cosmic radiation. If the boundary is more porous than we realized, what does this mean for the long-term habitability of planets like Earth? Could it also explain some of the anomalies in cosmic ray behavior observed by other missions? The probe's findings are reshaping our understanding of the heliosphere and its role in the solar system. Far from being a static barrier, the heliosphere is a dynamic, ever-changing region that interacts with the broader galaxy in ways we're only beginning to comprehend. As we continue to explore this boundary, we're uncovering clues about the Sun's influence on the interstellar medium and the broader cosmic environment. With these discoveries, the Parker Solar Probe is not only shedding light on the Sun's mysteries, but also revealing how our star is connected to the wider universe. What other secrets lie at the edge of the heliosphere, and how might these findings change our understanding of the Sun's place in the cosmos? Next, we'll turn our attention to another intriguing anomaly, the high-speed particle jets emanating from the Sun and their unexplained origins. Now, shifting our focus closer to the Sun itself, we encounter another fascinating anomaly, the high-speed particle jets that burst forth from our star. These jets, observed by the Parker Solar Probe, are streams of charged particles ejected at incredible speeds, often reaching hundreds of kilometers per second. What makes them so intriguing is not just their speed, but the fact that their origins remain shrouded in mystery. Scientists have long known that the Sun releases particles into space, but the discovery of these highly focused, high-speed jets has added a new layer of complexity to our understanding. Unlike the more diffuse solar wind, these jets are narrow, concentrated streams that seem to originate from specific regions on the Sun's surface. The probe's instruments have captured these jets in stunning detail, revealing their structure and behavior in ways never before possible. One of the most puzzling aspects of these jets is their unpredictability. They don't appear to follow a regular pattern or schedule, making them difficult to study and even harder to predict. Some jets last for just a few minutes, while others persist for hours. This irregularity has led scientists to question what triggers them in the first place. Are they caused by magnetic reconnection events, where the Sun's magnetic field lines snap and reconnect, releasing bursts of energy? Or could they be linked to the Sun's turbulent plasma flows, which churn and twist beneath its surface? Another mystery is the sheer energy these jets carry. The particles within them are accelerated to such high speeds that they can travel vast distances across the solar system. Some researchers speculate that these jets might play a role in shaping the solar wind, influencing how it flows and interacts with the planets. Others wonder if they could be contributing to the Sun's overall energy output, potentially affecting space weather and even Earth's climate. The Parker Solar Probe's observations have also revealed that these jets are not uniform. Some are hotter, denser, or faster than others, suggesting that different mechanisms might be at play. This variability has opened up new avenues of research as scientists try to piece together the conditions that give rise to these powerful phenomena. Could they be tied to the Sun's magnetic field dynamics, or perhaps even to deeper processes occurring within the star itself? As we continue to study these high-speed particle jets, one thing is clear: they are a testament to the Sun's complexity and the many mysteries it still holds. Each new observation brings us closer to understanding their origins, but for now, they remain one of the most enigmatic features of our star. What drives these jets, and how do they fit into the broader picture of solar activity? These are questions that will keep scientists and us fascinated for years to come. Next, we'll explore another intriguing anomaly, the Sun's connection to dark matter and the theories that attempt to explain this cosmic link. Now, let's venture into one of the most speculative and fascinating areas of solar research, the potential connection between the Sun's anomalies and dark matter. This theory, while still in its early stages, has sparked considerable interest among scientists, as it could provide a groundbreaking explanation for some of the Sun's most perplexing behaviors. The Parker Solar Probe's data has played a crucial role in fueling these discussions, offering new insights that challenge our understanding of both the Sun and the elusive nature of dark matter. Dark matter, as we know, is a mysterious substance that makes up about 27% of the universe. Unlike ordinary matter, it doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Yet, its presence is inferred through its gravitational effects on galaxies and other cosmic structures. So, how could something so intangible be connected to the Sun? Some researchers propose that dark matter particles might accumulate within the Sun's core, interacting in ways that could influence its energy production and magnetic activity. One intriguing idea is that dark matter particles could be captured by the Sun's immense gravitational pull, sinking into its core over time. Once there, these particles might annihilate or decay, releasing energy that could subtly alter the Sun's internal dynamics. This process could potentially explain some of the anomalies observed by the Parker Solar Probe, such as fluctuations in the Sun's energy output or irregularities in its magnetic field. While this theory is still speculative, it offers a tantalizing possibility that dark matter might be playing a hidden role in shaping the behavior of our closest star. Another angle explores the possibility that dark matter could affect the Sun's rotation. Observations have shown that the Sun's outer layers rotate at different speeds than its core, a phenomenon known as differential rotation. Some scientists suggest that dark matter particles, if present in sufficient quantities, could influence this rotation pattern by interacting with the Sun's plasma and magnetic fields. The Parker Solar Probe's detailed measurements of the Sun's magnetic activity and plasma flows have provided valuable data to test these hypotheses, though definitive answers remain elusive. The probe's findings have also raised questions about the Sun's role in the broader cosmic dance of dark matter. Could the Sun act as a natural laboratory for studying dark matter interactions? Some researchers believe that by analyzing the Sun's anomalies, we might uncover clues about the properties of dark matter itself. For instance, if dark matter particles are indeed interacting within the Sun, their signatures might be detectable in the form of subtle changes in solar emissions or magnetic activity. Of course, these theories are not without their challenges. Detecting dark matter's influence on the Sun requires incredibly precise measurements and a deep understanding of solar physics. The Parker Solar Probe's advanced instruments have brought us closer than ever to making these observations, but the data is complex and open to interpretation. As scientists continue to analyze the probe's findings, they are also developing new models and simulations to explore the potential dark matter connection. While the idea of dark matter influencing the Sun is still a topic of debate, it highlights the profound mysteries that remain in our understanding of the cosmos. The Parker Solar Probe's mission has not only deepened our knowledge of the Sun, but also opened the door to exploring connections between our star and the larger universe. As we continue to unravel these mysteries, one thing is certain: the Sun holds secrets that could reshape our understanding of both solar physics and the nature of dark matter. Next, we'll turn our attention to another captivating anomaly: the Sun's energy output variations and their potential impact on Earth. Now, shifting our focus to another intriguing aspect of the Sun's behavior, let's explore the variations in its energy output and what they could mean for our planet. The Parker Solar Probe has revealed that the Sun's energy output isn't as constant as we once thought. Instead, it fluctuates in ways that challenge our understanding of solar dynamics and raise important questions about how these changes might affect Earth. The Sun's energy, often referred to as solar irradiance, is the primary driver of Earth's climate and weather systems. Even small changes in this energy output can have significant consequences. The probe's observations have shown that these fluctuations are more complex than previously believed, with variations occurring on both short and long timescales. Some of these changes are tied to the Sun's natural cycles, like the 11-year solar cycle, but others appear to be more random and harder to predict. One of the most striking findings is the discovery of sudden dips and spikes in solar irradiance. These abrupt changes don't always align with known solar phenomena, such as sunspots or solar flares, leaving scientists puzzled about their origins. Some theories suggest that these variations could be linked to the Sun's internal processes, such as shifts in its magnetic fields or plasma flows. Others propose that external factors, like interactions with cosmic rays or even dark matter, might play a role. While the exact causes remain unclear, the implications for Earth are undeniable. For instance, a prolonged decrease in solar energy output could lead to cooler global temperatures, potentially triggering a mini ice age. On the other hand, a sudden increase could exacerbate global warming, accelerating the melting of polar ice caps and raising sea levels. The Parker Solar Probe's data has provided crucial insights into these possibilities, helping scientists refine their models and improve predictions about how the Sun's behavior might influence our climate. Another area of concern is the impact of solar energy variations on Earth's technological infrastructure. Solar storms, which are often associated with spikes in energy output, can disrupt satellites, power grids, and communication systems. By studying these fluctuations, researchers hope to develop better early warning systems to protect against such disruptions. The probe's detailed measurements of the Sun's magnetic activity and plasma flows have been instrumental in advancing this research, offering a clearer picture of how solar energy variations propagate through space. Interestingly, the probe's findings have also sparked discussions about the Sun's role in shaping Earth's long-term climate history. Some scientists believe that past fluctuations in solar energy output may have contributed to major climate events, such as the Little Ice Age during the 17th century. By analyzing the Sun's current behavior, researchers aim to uncover patterns that could help us understand these historical events and predict future climate trends. As we continue to study the Sun's energy output, one thing is clear: our star's behavior is far more dynamic and unpredictable than we once imagined. The Parker Solar Probe's mission has not only deepened our understanding of these variations, but also highlighted the intricate connection between the Sun and Earth. With each new discovery, we gain valuable insights into how our planet's climate and technology are shaped by the ever-changing energy of our closest star. Next, we'll delve into another fascinating anomaly: the massive plasma loops observed by the probe and their mysterious behavior. Now, turning our attention to one of the Sun's most visually stunning yet enigmatic features, let's dive into the phenomenon of plasma loops. The Parker Solar Probe has captured breathtaking images and data of these massive, arching structures that stretch across the Sun's surface, revealing behaviors that defy our current understanding of solar physics. These loops, composed of superheated plasma, are not just a spectacle to behold, they hold clues to some of the Sun's deepest mysteries. Plasma loops are essentially rivers of charged particles that flow along the Sun's magnetic field lines, creating colossal arches that can extend tens of thousands of kilometers into space. What makes them so fascinating is their dynamic and unpredictable nature. The probe's observations have shown that these loops are far from static. They twist, writhe, and sometimes even snap, releasing enormous amounts of energy in the process. This behavior has left scientists scratching their heads, as it doesn't always align with existing models of magnetic activity on the Sun. One of the most puzzling aspects of these loops is their temperature. While the sun's surface or photosphere hovers around 5,500 degrees Celsius, the plasma within these loops can reach temperatures exceeding 1 million degrees. This extreme heat is difficult to explain, especially since the loops are often located in regions of the sun's atmosphere that are cooler than their surroundings. Some theories suggest that the loops are heated by magnetic reconnection events, where magnetic field lines break and reconnect, releasing bursts of energy. Others propose that waves traveling through the sun's atmosphere, known as Alfvén waves, might play a role in transferring energy to the loops. The Parker Solar Probe has also observed that these loops are not uniformly distributed across the sun. Instead, they tend to cluster in active regions, often near sunspots, where the sun's magnetic field is particularly strong and complex. This clustering raises questions about how these loops form and why they appear in specific areas. Are they a byproduct of the sun's internal dynamo, or do they result from interactions between different layers of the sun's atmosphere? The probe's data is helping scientists piece together these puzzles, but many questions remain unanswered. Another intriguing observation is the way these loops interact with the solar wind. The probe has detected instances where plasma loops appear to funnel material into the solar wind, accelerating particles to incredible speeds. This process could help explain how the solar wind gains its energy, but the exact mechanisms are still unclear. Understanding this connection is crucial, as the solar wind plays a key role in shaping space weather and its impact on Earth. Perhaps the most dramatic aspect of plasma loops is their potential to trigger solar eruptions. When these loops become unstable, they can snap, releasing vast amounts of energy in the form of solar flares or coronal mass ejections. These events can have significant consequences for Earth, disrupting satellites, power grids, and communication systems. By studying the behavior of plasma loops, scientists hope to improve their ability to predict such eruptions and mitigate their effects. As we continue to unravel the mysteries of the sun's plasma loops, one thing is certain: these structures are more than just a cosmic light show. They are a window into the sun's complex magnetic environment and a key to understanding the forces that drive solar activity. The Parker Solar Probe's groundbreaking observations are bringing us closer to solving these puzzles. But as with so much about our star, the more we learn, the more questions arise. Next, we'll explore another captivating anomaly: the probe's detection of gamma-ray bursts from the sun and their unexplained origins. Now, shifting our focus to a phenomenon that has left scientists both fascinated and baffled, let's delve into the sun's gamma-ray burst. The Parker Solar Probe has made a startling discovery. Our sun, often thought of as a steady source of light and heat, occasionally emits powerful bursts of gamma rays, the most energetic form of light in the universe. These bursts are not only unexpected but also challenge our understanding of solar activity and the processes occurring within our star. Gamma-ray bursts are typically associated with cataclysmic events in deep space, such as the collapse of massive stars or the collision of neutron stars. So, detecting them from the sun is nothing short of extraordinary. The probe's instruments have captured these bursts, which last only a few seconds but release an astonishing amount of energy. What's even more puzzling is that these bursts don't seem to correlate with other known solar phenomena, like solar flares or coronal mass ejections. This raises the question: what exactly is causing them? One leading theory suggests that these gamma-ray bursts might be linked to the sun's magnetic field. As the sun's magnetic field lines twist and snap, they could accelerate particles to near light speeds, causing them to collide and produce gamma rays. Another possibility is that these bursts are the result of interactions between high-energy particles and the sun's atmosphere. However, neither theory fully explains the intensity or timing of these events, leaving scientists with more questions than answers. The Parker Solar Probe's observations have also revealed that these gamma-ray bursts are not evenly distributed across the sun. They tend to occur in regions with particularly strong magnetic activity, often near sunspots or active regions. This clustering suggests that the Sun's magnetic environment plays a crucial role in their formation, but the exact mechanisms remain elusive. Could these bursts be a sign of hidden processes deep within the Sun, or are they the result of interactions between the Sun's surface and its outer atmosphere? The probe's data is helping to narrow down the possibilities, but the mystery persists. Another intriguing aspect of these gamma-ray bursts is their potential impact on space weather. While they are brief, the energy they release could influence the behavior of the solar wind and other particles streaming from the Sun. This, in turn, could affect Earth's magnetosphere and even our technology, from satellites to communication systems. Understanding these bursts is not just an academic exercise. It has real-world implications for how we predict and prepare for solar activity. As we continue to study these enigmatic bursts, one thing is clear: the Sun still holds many secrets. The Parker Solar Probe's ability to observe these events up close is providing unprecedented insights, but each discovery seems to open the door to new questions. What triggers these bursts? How do they fit into the broader picture of solar activity? And what can they tell us about the fundamental processes that power our star? These are the questions that drive scientists forward, and the answers may reshape our understanding of the Sun and its influence on the solar system. Next, we'll turn our attention to another fascinating anomaly: the probe's findings on magnetic reconnection events and their role in shaping the Sun's behavior. Moving deeper into the Sun's magnetic mysteries, let's explore another groundbreaking discovery made by the Parker Solar Probe: magnetic reconnection events. These events are like cosmic short circuits, where the Sun's magnetic field lines break apart and reconnect, releasing enormous amounts of energy in the process. While scientists have long known about magnetic reconnection, the probe's observations have revealed just how dynamic and unpredictable these events can be, offering new clues about their role in shaping solar activity. Magnetic reconnection occurs when the Sun's magnetic field lines, which are constantly shifting and twisting, snap and realign. This process can release energy equivalent to millions of hydrogen bombs in just a fraction of a second. The Parker Solar Probe has captured these events in unprecedented detail, showing how they can trigger solar flares, coronal mass ejections, and even the acceleration of solar wind particles. But what makes these findings so intriguing is that they don't always follow the patterns scientists expected. One of the probe's most surprising discoveries is that magnetic reconnection events can happen much closer to the Sun's surface than previously thought. Earlier models suggested these events primarily occurred in the Sun's outer atmosphere, but the probe's data shows they can also take place in the lower corona, just above the Sun's visible surface. This challenges our understanding of where and how energy is released on the Sun, suggesting that the processes driving solar activity are far more complex than we imagined. Another puzzling aspect is the speed at which these reconnection events occur. The probe has observed instances where magnetic field lines snap and reconnect almost instantaneously, releasing energy in bursts that are difficult to predict. This unpredictability makes it harder for scientists to model solar activity accurately, especially when it comes to forecasting space weather events that could impact Earth. For example, a sudden reconnection event could trigger a solar flare powerful enough to disrupt satellite communications or even power grids on our planet. The Parker Solar Probe has also revealed that magnetic reconnection isn't always a one-time event. In some cases, the same region of the Sun's magnetic field can undergo multiple reconnections in quick succession, creating a cascade of energy releases. This phenomenon, known as bursty reconnection, adds another layer of complexity to our understanding of solar dynamics. It suggests that the Sun's magnetic field is far more turbulent and interconnected than we once believed, with small-scale events potentially triggering larger-scale consequences. But why does this matter? Beyond the scientific curiosity, understanding magnetic reconnection is crucial for predicting solar storms and their impact on Earth. These events are a key driver of space weather, which can affect everything from satellite operations to astronaut safety. By studying how and where reconnection occurs, scientists hope to improve their ability to forecast solar activity, giving us more time to prepare for potential disruptions. As we piece together the puzzle of magnetic reconnection, one thing is clear: the Sun's magnetic field is a dynamic and ever-changing force. The Parker Solar Probe's observations are shedding light on these processes, but each discovery seems to reveal new questions. What triggers these reconnection events? How do they influence the Sun's overall behavior? And what can they tell us about the fundamental physics of our star? These are the questions that keep scientists probing deeper into the Sun's secrets, and the answers could transform our understanding of the solar system. Now let's turn our attention to another captivating anomaly: the probe's findings on coronal mass ejections and why they sometimes defy prediction models. Shifting our focus to another fascinating discovery, let's dive into the Parker Solar Probe's findings on coronal mass ejections, or CME. These massive bursts of solar material and magnetic fields are some of the most dramatic events in our solar system, capable of hurling billions of tons of charged particles into space at incredible speeds. While scientists have studied CMEs for decades, the probe's close-up observations have revealed surprising details about their behavior, challenging our ability to predict them accurately. Coronal mass ejections originate from the Sun's corona, the outermost layer of its atmosphere. They often occur alongside solar flares, but unlike flares, which release energy in the form of light and radiation, CMEs eject vast amounts of plasma and magnetic fields. When these ejections reach Earth, they can interact with our planet's magnetic field, creating stunning auroras, but also posing risks to satellites, power grids, and even astronauts. Understanding CMEs is crucial for protecting our technology and infrastructure, but the Parker Solar Probe has shown that predicting them is far from straightforward. One of the probe's key discoveries is that not all CMEs follow the same pattern. While some are slow and steady, others are fast and explosive, with speeds exceeding millions of miles per hour. The probe's data has revealed that the Sun's magnetic field plays a critical role in determining the speed and intensity of these ejections. However, the exact mechanisms behind these differences remain unclear. For instance, some CMEs seem to stall or change direction unexpectedly, making it difficult to forecast their path and impact on Earth. Another puzzling aspect is the timing of these events. While scientists have identified certain triggers, such as magnetic reconnection or the destabilization of solar filaments, the probe has observed CMEs that appear to occur without any obvious cause. This unpredictability complicates efforts to develop reliable prediction models, as current tools often rely on identifying specific precursors. The Parker Solar Probe's observations suggest that the Sun's magnetic field is far more chaotic and interconnected than previously thought, with small-scale changes potentially leading to large-scale eruptions. The probe has also shed light on the structure of CMEs, revealing that they are not uniform blobs of plasma but rather complex, twisted formations. These structures, known as magnetic flux ropes, can carry immense amounts of energy and interact with the solar wind in unexpected ways. Sometimes these interactions can amplify the effects of a CME, while other times they can weaken it. This variability makes it even harder to predict how a CME will behave as it travels through space. But why do these findings matter? Beyond the scientific intrigue, improving our ability to predict CMEs is essential for safeguarding modern technology. A powerful CME directed at Earth could disrupt satellite communications, knock out power grids, and even endanger astronauts in space. By studying the Sun up close, the Parker Solar Probe is helping scientists refine their models and develop better tools for forecasting these events. However, the probe's data also highlights just how much we still have to learn about the sun's behavior. As we continue to unravel the mysteries of coronal mass ejections, one thing is certain: the sun is far more dynamic and unpredictable than we once believed. The Parker Solar Probe's observations are providing invaluable insights, but each discovery seems to raise new questions. What triggers these massive eruptions? How do they interact with the solar wind, and can we ever predict them with certainty? These are the challenges that drive solar science forward, and the answers could transform our understanding of space weather. Now, let's explore another intriguing anomaly: the probe's discovery of solar tornadoes and their potential connection to other solar phenomena. Moving deeper into the sun's mysteries, let's turn our attention to one of the most visually striking phenomena observed by the Parker Solar Probe: solar tornadoes. These swirling, towering structures of plasma and magnetic fields are not only breathtaking to behold, but also hold critical clues about the sun's dynamic behavior and its connection to other solar anomalies. Solar tornadoes, as the name suggests, resemble the tornadoes we see on Earth, but on a vastly larger and more energetic scale. These massive spirals of superheated plasma can stretch tens of thousands of miles into the sun's atmosphere, with temperatures reaching millions of degrees. Unlike Earth's tornadoes, which are driven by wind and pressure differences, solar tornadoes are powered by the sun's intense magnetic fields. These fields twist and churn, creating vortices that pull plasma upward from the sun's surface into its outer atmosphere, or corona. The Parker Solar Probe's close-up observations have revealed that these tornadoes are not just isolated events, but are intricately linked to other solar phenomena. For instance, they often form near sunspots, regions of intense magnetic activity on the sun's surface. Sunspots are known to be hotspots for solar flares and coronal mass ejections, and the probe's data suggests that solar tornadoes may play a role in triggering or amplifying these events. The swirling motion of the tornadoes can destabilize the sun's magnetic field, creating conditions ripe for explosive releases of energy. One of the most intriguing aspects of solar tornadoes is their potential connection to the sun's mysterious heating mechanisms. The corona, the sun's outer atmosphere, is hundreds of times hotter than the surface below, a fact that has puzzled scientists for decades. The probe's observations indicate that solar tornadoes may contribute to this heating by transferring energy from the sun's surface to its corona. As the tornadoes twist and rise, they carry heat and plasma upward, potentially helping to explain why the corona is so much hotter than the layers beneath it. But the mysteries don't end there. The Parker Solar Probe has also detected that solar tornadoes can interact with the solar wind, the stream of charged particles constantly flowing from the sun. These interactions can alter the speed and direction of the solar wind, creating ripples that travel across the solar system. In some cases, these changes can even affect space weather near Earth, influencing the behavior of auroras and potentially impacting satellite operations. What makes solar tornadoes even more fascinating is their unpredictability. While scientists have identified certain patterns, such as their tendency to form near sunspots, the exact conditions that give rise to these structures remain unclear. The probe's data has shown that solar tornadoes can appear suddenly and disappear just as quickly, making them difficult to study in detail. This unpredictability underscores the complexity of the sun's magnetic environment and highlights the challenges of understanding its behavior. So, why do solar tornadoes matter? Beyond their scientific intrigue, these phenomena offer a window into the sun's inner workings. By studying them, scientists hope to uncover new insights into the sun's magnetic field, its heating mechanisms, and its influence on space weather. Each discovery brings us closer to answering fundamental questions about our star and its impact on the solar system. As we continue to explore the sun's secrets, solar tornadoes remind us of the sheer power and complexity of our nearest star. They are not just awe-inspiring spectacles, but also key pieces of the puzzle in understanding the sun's behavior. And as the Parker Solar Probe continues its mission, we can expect even more revelations about these swirling giants and their role in the grand tapestry of solar activity. Now let's shift our focus to another captivating anomaly, the probe's observations of plasma instabilities and their implications for solar physics. Turning our gaze to another layer of the Sun's enigmatic behavior, let's delve into the probe's groundbreaking observations of plasma instabilities. These phenomena, though less visually dramatic than solar tornadoes, are no less significant in unraveling the Sun's complex dynamics. Plasma, the fourth state of matter, dominates the Sun's atmosphere, and its behavior is anything but predictable. The Parker Solar Probe has captured instances where this superheated, electrically charged gas behaves in ways that defy our current understanding, revealing a world of chaos and complexity. One of the most striking findings is the presence of plasma instabilities, sudden, erratic changes in the behavior of the Sun's plasma. These instabilities can manifest as rapid fluctuations in temperature, density, or magnetic field strength, often occurring without warning. Imagine a pot of water on the verge of boiling, where bubbles form and burst unpredictably. Now scale that up to the Sun, where the bubbles are massive structures of plasma, and you begin to grasp the scale of these instabilities. The probe's instruments have detected these fluctuations in regions where the Sun's magnetic fields are particularly intense, suggesting a deep connection between magnetic activity and plasma behavior. What makes these instabilities so intriguing is their potential role in shaping the Sun's atmosphere and influencing space weather. For instance, the probe has observed that plasma instabilities can trigger waves of energy that ripple through the Sun's corona. These waves, known as magnetohydrodynamic waves, carry energy across vast distances and may contribute to the mysterious heating of the corona. While scientists have long suspected that such waves play a role in coronal heating, the probe's data provides some of the most direct evidence yet, linking plasma instabilities to this enduring puzzle. But the implications don't stop there. Plasma instabilities also appear to play a role in the acceleration of the solar wind. The probe has detected that these instabilities can create localized bursts of energy, propelling charged particles to incredible speeds. This process, known as particle acceleration, is a key driver of the solar wind, the stream of particles that flows outward from the Sun and fills the solar system. By studying these instabilities, scientists hope to better understand how the solar wind is generated and how it evolves as it travels through space. Another fascinating aspect of plasma instabilities is their potential to disrupt the Sun's magnetic field. The probe's observations suggest that these instabilities can cause sudden reconfigurations of the magnetic field, leading to phenomena like magnetic reconnection. This process, where magnetic field lines break and reconnect, is a major source of solar flares and coronal mass ejections. By shedding light on how plasma instabilities contribute to magnetic reconnection, the probe's findings could revolutionize our understanding of these explosive events and their impact on space weather. Yet, despite these insights, plasma instabilities remain shrouded in mystery. The probe's data has revealed that these phenomena are highly localized and short-lived, making them difficult to study in detail. Moreover, the exact mechanisms that drive these instabilities are still unclear. Are they caused by turbulence in the Sun's magnetic field? Do they arise from interactions between different layers of the Sun's atmosphere? These are questions that scientists are still working to answer, and each new observation from the Parker Solar Probe brings us closer to solving the puzzle. So, why do plasma instabilities matter? Beyond their scientific significance, these phenomena offer a glimpse into the fundamental processes that govern the Sun's behavior. By studying them, we gain a deeper understanding of how energy is transferred and transformed within our star, from its surface to its outer atmosphere. This knowledge not only advances our understanding of the Sun, but also helps us predict and mitigate the effects of space weather on Earth and our technology. As we continue to explore the sun's secrets, plasma instabilities remind us of the intricate interplay of forces at work in our star. They are a testament to the sun's complexity and the challenges of unraveling its mysteries. And with each new discovery, the Parker Solar Probe brings us one step closer to understanding the dynamic, ever-changing nature of our nearest star. Now, let's shift our focus to another captivating anomaly: the probe's findings on twisted magnetic fields and their role in solar activity. Now, let's unravel another layer of the sun's magnetic mysteries: the twisted magnetic fields. These intricate spirals of magnetic energy are not just fascinating to observe, they play a crucial role in shaping the sun's activity and influencing space weather. The Parker Solar Probe has provided unprecedented insights into these twisted fields, revealing a dynamic and often chaotic interplay of forces that challenge our understanding of solar physics. Twisted magnetic fields, also known as magnetic helicity, occur when the sun's magnetic field lines become coiled or braided, much like a twisted rope. This twisting happens due to the sun's rotation and the turbulent motion of plasma in its atmosphere. The probe's instruments have captured these structures in stunning detail, showing how they can stretch, snap, and reconnect, releasing vast amounts of energy in the process. These events are not just visually striking, they are key drivers of solar flares and coronal mass ejections, the explosive phenomena that can send charged particles hurtling toward Earth. One of the most intriguing findings is how these twisted fields contribute to the sun's magnetic reconnection events. When magnetic field lines become too twisted, they can snap and realign, releasing energy in the form of heat, light, and particle acceleration. The probe has observed this process in action, providing critical data on how these reconnections occur and how they influence the sun's atmosphere. For instance, twisted fields near the sun's surface can trigger sudden bursts of energy that heat the corona, helping to explain why this outer layer is so much hotter than the surface below. But the story doesn't end there. Twisted magnetic fields also play a role in the formation of sunspots, those dark patches on the sun's surface that mark areas of intense magnetic activity. The probe's data suggests that the degree of twisting in these fields can determine the size and stability of sunspots, as well as their potential to produce solar flares. By studying these structures, scientists hope to improve their ability to predict solar activity and its impact on Earth. Another fascinating aspect of twisted magnetic fields is their connection to the solar wind. The probe has detected that these fields can act as channels, guiding charged particles away from the sun and into space. In some cases, the twisting motion can even accelerate particles to incredible speeds, contributing to the high energy streams that make up the solar wind. This discovery sheds light on how the sun's magnetic fields shape the flow of particles throughout the solar system, influencing everything from the auroras on Earth to the conditions in deep space. Despite these breakthroughs, twisted magnetic fields remain a source of mystery. The probe's observations have shown that these structures are highly dynamic, changing shape and intensity over short periods. This unpredictability makes them difficult to study and model, leaving many questions unanswered. For example, what causes the twisting to become unstable? How do these fields interact with other solar phenomena like plasma instabilities or magnetic switchbacks? These are questions that scientists are eager to explore, and each new observation from the Parker Solar Probe brings us closer to understanding the sun's magnetic dance. So, why do twisted magnetic fields matter? Beyond their role in solar activity, these structures offer a window into the fundamental processes that govern the sun's behavior. By studying them, we gain a deeper understanding of how energy is stored, released, and transferred within our star. This knowledge not only advances our understanding of the sun, but also helps us predict and prepare for the effects of space weather on Earth and our technology. As we continue to explore the sun's magnetic mysteries, twisted fields remind us of the intricate and ever-changing nature of our star. They are a testament to the complexity of solar physics and the challenges of unraveling its secrets. And with each new discovery, the Parker Solar Probe brings us one step closer to understanding the dynamic forces that shape our solar system. Next, we'll dive into another captivating anomaly, the probe's findings on particle acceleration zones and their role in shaping the Sun's energetic environment. Now, shifting our focus to another remarkable discovery, let's explore the Sun's particle acceleration zones. These regions, observed by the Parker Solar Probe, are areas where particles are propelled to extreme speeds, often reaching velocities that defy our current understanding of solar physics. These zones are not just fascinating, they hold the key to unraveling how the Sun generates and releases energy into the solar system. The probe's instruments have revealed that these acceleration zones are scattered throughout the Sun's atmosphere, particularly in the corona and the solar wind. In these regions, charged particles such as electrons and protons are accelerated to incredible speeds, sometimes approaching a significant fraction of the speed of light. This process is driven by the Sun's intense magnetic fields and the turbulent plasma environment, which create conditions ripe for particle acceleration. One of the most intriguing aspects of these zones is their connection to solar flares and coronal mass ejections. During these explosive events, particles are funneled through magnetic fields and accelerated to extreme energies. The probe's data has shown that these acceleration zones often coincide with areas of intense magnetic activity, such as sunspots or regions where magnetic reconnection occurs. This suggests that the Sun's magnetic fields play a crucial role in powering these high-speed particle streams. But how exactly does this acceleration happen? Scientists believe that several mechanisms are at work. One theory involves magnetic reconnection, where twisted magnetic field lines snap and realign, releasing energy that propels particles to high speeds. Another possibility is the presence of shock waves, which can form when fast-moving plasma collides with slower material, creating a wave front that accelerates particles. The probe's observations have provided evidence for both processes, offering a more comprehensive picture of how these acceleration zones operate. What makes these zones even more fascinating is their impact on the solar wind. The particles accelerated in these regions contribute to the high energy streams that make up the solar wind, which flows outward from the Sun and interacts with planets including Earth. By studying these acceleration zones, scientists can better understand how the solar wind is formed and how it evolves as it travels through the solar system. This knowledge is crucial for predicting space weather and its effects on satellites, communication systems, and even power grids on Earth. Despite these insights, particle acceleration zones remain a source of mystery. The probe's data has shown that these regions are highly dynamic, with particles being accelerated in bursts rather than continuously. This unpredictability makes them challenging to study and model, leaving many questions unanswered. For instance, what triggers these bursts of acceleration? How do the particles maintain their high speeds over vast distances? These are questions that scientists are eager to explore, and each new observation from the Parker Solar Probe brings us closer to understanding the Sun's energetic environment. So, why do particle acceleration zones matter? Beyond their role in shaping the solar wind, these regions offer a glimpse into the fundamental processes that drive the Sun's activity. By studying them, we gain a deeper understanding of how energy is transferred and transformed within our star. This knowledge not only advances our understanding of the Sun, but also helps us predict and prepare for the effects of space weather on Earth and our technology. As we continue to explore the Sun's mysteries, particle acceleration zones remind us of the incredible forces at work in our star. They are a testament to the complexity of solar physics and the challenges of unraveling its secrets. And with each new discovery, the Parker Solar Probe brings us one step closer to understanding the dynamic forces that shape our solar system. Next, we'll turn our attention to another captivating anomaly, the sun's unexplained brightness variations and what they reveal about our star's behavior. Now, let's turn our gaze to another intriguing mystery, the sun's unexplained brightness variations. The Parker Solar Probe has captured data revealing that the sun's brightness isn't constant. It fluctuates in ways that challenge our current understanding of solar behavior. These variations aren't just minor blips, they represent significant shifts in the sun's energy output, raising questions about what drives these changes and how they impact the solar system. One of the most puzzling aspects of these brightness fluctuations is their irregularity. Unlike the predictable patterns of the sun's 11-year solar cycle, these variations occur sporadically and don't always align with known solar phenomena. For instance, the probe has observed periods where the sun's brightness increases or decreases without a clear connection to sunspots, solar flares, or other visible activity. This unpredictability has left scientists scratching their heads, as it suggests there are hidden mechanisms at play that we have yet to uncover. So, what could be causing these brightness changes? One leading theory points to the sun's magnetic fields. The probe's data indicates that shifts in magnetic activity, particularly in the corona, could influence how much light and energy the sun emits. When magnetic fields become tangled or reconfigure, they might alter the flow of energy through the sun's layers, leading to temporary changes in brightness. Another possibility involves the sun's internal dynamics, such as changes in the rate of nuclear fusion or the movement of plasma within its core. These internal shifts could create ripples that affect the sun's surface and ultimately its brightness. The implications of these brightness variations extend far beyond the sun itself. Changes in the sun's energy output can have a direct impact on Earth's climate and space weather. For example, prolonged periods of reduced brightness could lead to cooler temperatures on our planet, while increased brightness might contribute to warming. Understanding these fluctuations is crucial for predicting their effects on Earth's environment and technological systems, such as satellites and power grids. What makes this anomaly even more fascinating is its connection to other solar mysteries. The probe's observations suggest that brightness variations might be linked to phenomena like solar wind acceleration and magnetic reconnection events. This interconnectedness highlights the complexity of the sun's behavior and underscores the importance of studying it as a dynamic, ever-changing system. Each new piece of data from the Parker Solar Probe brings us closer to unraveling these connections and understanding the sun's full range of activity. Despite the progress made, many questions remain. Why do these brightness changes occur so unpredictably? Are they driven by internal processes, magnetic activity, or a combination of factors? And how do they influence the broader solar system? These are the questions that scientists are working tirelessly to answer, using the wealth of data provided by the Parker Solar Probe. As we continue to explore the sun's mysteries, its unexplained brightness variations remind us of the complexity and dynamism of our star. They challenge us to rethink our assumptions and push the boundaries of solar physics. And with each new discovery, we gain a deeper appreciation for the forces that shape not only the sun, but also the world we live in. Next, we'll delve into the final anomaly on our list, the sun's connection to cosmic rays and the unanswered questions it raises about the universe beyond our solar system. Now, let's shift our focus to one of the most enigmatic aspects of the sun's behavior, its connection to cosmic rays. The Parker Solar Probe has uncovered fascinating data about how the sun influences these high-energy particles which travel through space at nearly the speed of light. Cosmic rays are not just random space debris, they are charged particles, primarily protons and atomic nuclei, that originate from various sources, including the sun. But what makes this connection so puzzling is the sun's ability to both generate and modulate these rays in ways that defy our current understanding. One of the probe's most surprising discoveries is that the sun doesn't just emit cosmic rays, it also acts as a shield, deflecting some of them away from the inner solar system. This dual role has left scientists intrigued. On one hand, the sun's magnetic fields and solar wind create a protective bubble known as the heliosphere, which blocks a significant portion of cosmic rays from entering. On the other hand, the sun itself produces low-energy cosmic rays, particularly during solar flares and coronal mass ejections. This duality raises questions about how the sun balances its role as both a source and a barrier for these particles. The probe's data has also revealed that the intensity of cosmic rays varies with the sun's activity cycle. During periods of high solar activity, such as solar maximums, the sun's magnetic field strengthens, reducing the number of cosmic rays that reach Earth. Conversely, during solar minimums, when the sun is quieter, more cosmic rays penetrate the heliosphere. This inverse relationship suggests a complex interplay between the sun's magnetic activity and the flow of cosmic rays, but the exact mechanisms remain unclear. What's even more baffling is the origin of the highest energy cosmic rays. While the sun produces lower energy cosmic rays, the most energetic ones are thought to come from outside our solar system, possibly from supernova or other extreme cosmic events. Yet the Parker Solar Probe has detected anomalies in how these high-energy particles interact with the sun's magnetic fields. Some particles appear to be accelerated or redirected in unexpected ways, hinting at processes we don't yet fully understand. Could the sun be playing a more significant role in shaping cosmic rays than we've realized? Or are there hidden forces at work that we're only beginning to uncover? The implications of these findings are profound. Cosmic rays are not just a curiosity, they have real-world effects. On Earth, they can interfere with satellite communications, disrupt power grids, and even pose health risks to astronauts and airline crews. Understanding how the sun influences cosmic rays is crucial for predicting and mitigating these impacts. Moreover, studying cosmic rays can provide insights into the broader universe as they carry information about distant cosmic events and the structure of interstellar space. As we piece together the sun's role in cosmic ray generation and modulation, we're reminded of how interconnected the cosmos truly is. The Parker Solar Probe's findings challenge us to rethink our understanding of the sun's influence on the solar system and beyond. Each new discovery brings us closer to unraveling the mysteries of cosmic rays and their relationship with our star. But as with so many of the sun's anomalies, the answers often lead to even more questions, driving us to explore further and dig deeper into the secrets of the universe. Next, we'll reflect on the Parker Solar Probe's groundbreaking discoveries and how they've reshaped our understanding of the sun and the mysteries it holds. As we continue to explore the mysteries of cosmic rays, the Parker Solar Probe's findings have opened up a new frontier of questions that challenge our understanding of the sun's role in the cosmos. One of the most intriguing puzzles is the sun's ability to both generate and deflect cosmic rays, a duality that seems almost contradictory. How can the same star that produces these high-energy particles also act as a shield, preventing others from reaching us? This paradox lies at the heart of the cosmic ray mystery, and the probe's data has only deepened the intrigue. One of the key revelations from the probe is the discovery of unexpected patterns in how cosmic rays interact with the sun's magnetic fields. While we've long known that the sun's magnetic activity influences the flow of these particles, the probe has detected anomalies that suggest there's more to the story. For instance, some cosmic rays appear to be accelerated to even higher energies as they pass near the sun, a phenomenon that current models can't fully explain. Could the sun's magnetic fields be acting as a cosmic particle accelerator, boosting the energy of these rays in ways we've never anticipated? Or are there other hidden forces at play that we're only beginning to detect? Another baffling aspect is the origin of the highest energy cosmic rays. While the Sun is known to produce lower energy cosmic rays, the most energetic ones are thought to come from distant cosmic events like supernova or black hole collisions. Yet, the Parker Solar Probe has observed that some of these high-energy particles behave in ways that don't align with our expectations. Instead of being deflected by the Sun's magnetic fields, some seem to be drawn toward it, as if the Sun has a gravitational or magnetic pull that we don't yet understand. This raises the possibility that the Sun might be influencing cosmic rays in ways that extend far beyond our current theories. The probe's data has also highlighted the complexity of the Sun's relationship with cosmic rays over time. During periods of high solar activity, the Sun's magnetic field strengthens, creating a more effective barrier against incoming cosmic rays. But during quieter periods, known as solar minimums, the barrier weakens, allowing more cosmic rays to penetrate the heliosphere. This cyclical pattern suggests a delicate balance between the Sun's magnetic activity and the flow of cosmic rays, but the exact mechanisms behind this balance remain elusive. Why does the Sun's influence on cosmic rays fluctuate so dramatically? And what does this tell us about the broader dynamics of our solar system? These unanswered questions have far-reaching implications. Cosmic rays are not just a scientific curiosity, they have real-world effects on technology, climate, and even human health. Understanding how the Sun shapes their behavior could help us better predict and mitigate their impacts, from protecting satellites and power grids to safeguarding astronauts on long-duration space missions. Moreover, studying cosmic rays offers a unique window into the broader universe, as they carry information about distant cosmic events and the structure of interstellar space. As we reflect on the Parker Solar Probe's groundbreaking discoveries, it's clear that the Sun's connection to cosmic rays is far more complex than we once thought. Each new finding challenges us to rethink our understanding of the Sun's role in the cosmos and pushes us to explore further. The probe's data has not only deepened the mystery of cosmic rays, but also reminded us of how much we still have to learn about our star and its place in the universe. With every question answered, new ones emerge, driving us to continue our quest for knowledge and uncover the secrets of the cosmos. As we turn the page on this chapter of cosmic exploration, the Parker Solar Probe's legacy stands as a testament to human ingenuity and our unrelenting curiosity about the universe. This mission has not only rewritten the textbooks on solar science, but has also opened our eyes to the profound mysteries that still surround our closest star. From the Sun's scorching corona to its enigmatic magnetic fields, the probe has delivered insights that have fundamentally reshaped our understanding of the Sun and its influence on the solar system. One of the most remarkable aspects of the probe's legacy is how it has challenged long-held assumptions. Before its journey, many of our theories about the Sun were based on observations made from a distance. But the Parker Solar Probe dared to go where no spacecraft had gone before, venturing into the Sun's corona and collecting data in the most extreme conditions imaginable. This bold approach has revealed phenomena that were previously invisible to us, such as the sudden reversals in the Sun's magnetic field, known as switchbacks, and the unexpected acceleration of solar wind particles. These discoveries have forced scientists to rethink how the Sun's atmosphere and magnetic fields operate, pushing the boundaries of our knowledge. Beyond its scientific achievements, the probe has also inspired a new generation of missions aimed at unraveling the Sun's secrets. Its success has demonstrated the value of daring, high-risk missions that push the limits of technology and human ambition. By proving that we can design spacecraft capable of withstanding the Sun's intense heat and radiation, the Parker Solar Probe has paved the way for future explorers to delve even deeper into the mysteries of our solar system. It's a reminder that the pursuit of knowledge often requires us to take bold steps into the unknown. Perhaps the most enduring legacy of the Parker Solar Probe is the way it has deepened our appreciation for the Sun's complexity. Far from being a simple ball of gas, the Sun is a dynamic, ever-changing entity with a profound influence on the cosmos. Its magnetic fields, solar winds, and energetic particles shape the environment of our solar system, affecting everything from the planets to the cosmic rays that travel through space. The probe's findings have shown us that the Sun is not just a star. It's a cosmic engine driving processes that extend far beyond its surface. As we look to the future, the Parker Solar Probe's discoveries will continue to guide our exploration of the Sun and its mysteries. They remind us that even the most familiar objects in the universe can hold surprises, waiting to be uncovered by those willing to ask the right questions and push the boundaries of what's possible. The probe's legacy is not just a collection of data. It's a call to keep exploring, to keep questioning, and to keep reaching for the stars. And as we do, we'll undoubtedly uncover even more wonders that will reshape our understanding of the cosmos once again. As we step into the next chapter of solar exploration, the Parker Solar Probe has not only answered questions but also sparked new ones, paving the way for future missions to continue unraveling the Sun's secrets. One of the most exciting developments on the horizon is the European Space Agency's Solar Orbiter, a mission designed to complement the Parker Solar Probe's findings. While the Parker Probe focuses on the Sun's corona and solar wind, Solar Orbiter will provide high-resolution images of the Sun's surface and polar regions, offering a more complete picture of our star's behavior. Together, these missions will help scientists piece together the complex puzzle of solar dynamics from the surface to the outer atmosphere, but the mysteries don't stop there. Despite the groundbreaking discoveries made by the Parker Solar Probe, many questions remain unanswered. For instance, why does the Sun's corona reach temperatures millions of degrees hotter than its surface? What exactly causes the sudden reversals in the Sun's magnetic field, known as switchbacks, and how do solar wind particles accelerate to such incredible speeds? These are just a few of the puzzles that continue to baffle scientists, driving the need for even more advanced missions in the future. Looking ahead, NASA and other space agencies are already planning the next generation of solar probes. These missions aim to build on the Parker Solar Probe's success by incorporating even more advanced technology, such as improved heat shields and more sensitive instruments. Some proposals even suggest sending probes closer to the Sun than ever before, venturing into regions where the heat and radiation are even more extreme. The goal is to gather data that will help us understand not just the Sun, but also how its behavior affects the entire solar system, from the planets to the farthest reaches of the heliosphere. Another area of focus for future missions is the Sun's connection to space weather. Solar flares and coronal mass ejections can have a significant impact on Earth, disrupting satellites, power grids, and even communication systems. By studying these phenomena in greater detail, scientists hope to develop better prediction models, giving us more time to prepare for potential disruptions. This research could have real-world implications, helping to protect our increasingly technology-dependent society from the Sun's unpredictable outbursts. Yet, even as we plan these ambitious missions, it's important to remember that the Sun is just one star in a vast universe. The lessons we learn from studying our own star could also shed light on other stars and their behavior. For example, understanding how the Sun's magnetic fields work could help us better interpret observations of distant stars, potentially revealing new insights into the life cycles of stars and the formation of planetary systems. As we look to the future, one thing is clear: the Parker Solar Probe has set the stage for a new era of solar exploration. Its discoveries have not only deepened our understanding of the Sun, but also inspired a wave of new missions aimed at solving the mysteries that remain. From the Sun's scorching corona to its enigmatic magnetic fields, there's still so much to learn. And as we continue to push the boundaries of science and technology, we'll undoubtedly uncover even more wonders that will reshape our understanding of the cosmos once again. The journey is far from over, and the next chapter promises to be just as thrilling as the last. As we bring our journey through the 25 unexplained space anomalies to a close, it's clear that the Parker Solar Probe has not only deepened our understanding of the Sun, but also opened up a universe of new questions. From the scorching mystery of the Sun's corona to the baffling behavior of solar wind particles, each anomaly reminds us just how much we still have to learn about our closest star. The probe's groundbreaking discoveries have reshaped our understanding of solar physics, revealing a dynamic and complex system that defies many of our expectations. These findings are more than just scientific milestones, they're stepping stones toward a deeper connection with the cosmos. The Parker Solar Probe has shown us that the Sun is far from a static ball of fire. It's a living, breathing entity full of surprises and secrets waiting to be uncovered. Its magnetic fields twist and turn in ways we can't yet fully explain. Its plasma loops and particle jets challenge our understanding of energy and motion, and its influence stretches far beyond its surface, shaping the very fabric of our solar system. Each anomaly the probe has uncovered is a reminder that the universe is far stranger and more wondrous than we often imagine, but the story doesn't end here. The Parker Solar Probe has set the stage for a new era of exploration, inspiring missions that will push the boundaries of what we know even further. As we continue to study these anomalies, we're not just learning about the Sun, we're learning about the fundamental forces that govern the universe itself. Every discovery brings us closer to answering some of the biggest questions in science, from the nature of space weather to the origins of cosmic rays. So, as we reflect on these 25 mysteries, let's not forget the most important lesson of all. Curiosity is the driving force behind every great discovery. The Parker Solar Probe has shown us that even the most familiar objects in the sky can hold secrets that challenge our understanding. And as we look to the future, there's no doubt that more surprises await us. Whether you're a seasoned space enthusiast or just beginning to explore the wonders of the cosmos, remember that every question we ask brings us one step closer to unlocking the mysteries of the universe. If you've enjoyed this journey through the Sun's most puzzling anomalies, don't forget to like this video, subscribe to the channel, and hit the notification bell so you never miss an update. The cosmos is full of wonders, and together we'll keep exploring them one mystery at a time. Stay curious, and who knows, maybe the next great discovery will be inspired by you. Until next time, keep looking.